Good afternoon, everybody. Hey, I have a fun one for you today. It's a third degree polynomial, and it has two irrational solutions and then one integer solution. Now, of course, the integer solution is easy to check, but I want to spend some time going through the check, which I think very few teachers these days enforce. Now, if you'll take a look at this polynomial, it's a third degree polynomial. And you can use something called the rational zero theorem. And if the polynomial has a rational zero, it'll be a divisor of this constant term. In this case, I made it easy. 1 only has two divisors, namely itself and -1. Now, it turns out -1 is a solution. And I didn't want to go to too much trouble on this because the key to this is just the hard part of actually checking the rationals. But you can see the irrationals, excuse me. If you put -1 right here, you get -1. -2 is -3. If you put -1 right here, this would be -3 plus 3. So -1 is indeed a solution. And it turns out you can use that along with synthetic division to find these other two irrational zeros. Now, the only one I want to go through today is just checking that 3 plus √5/2 is a solution. Now, this is a tough problem, even if it's just a second degree or a quadratic expression. But I don't know, I guess a lot of y'all have done this, but just look at the effort involved here. So here's 3 plus √5/2 is just one of the irrational solutions. And so I'm going to take this object right here, 3 plus √5/2, and substitute it everywhere I see an x in our original. Okay. So there's three locations where I have to place 3 plus √5/2. And you can see I've done that right here. Okay. 3 plus √5/2 quantity cubed, 3 plus √5/2 quantity squared, and then -2 times 3 plus √5/2. So this first part was just physical substitution. I just physically place it there to get started, and that's the way to start a problem like this. But what's tough about this is now you have a binomial cubed, and you have no choice right here but to use this result: a plus b quantity cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. And if you're going to do this manually without a calculator, that's the only way to do this. And so I even did a few of the steps here in my head. This 2 downstairs is the same as 1/2 cubed. The 2 in the denominator is the same as 1/2 cubed. So you can just put the 1/8 out front. Makes the expansion a little bit easier. And a very similar process here. There's already a -2 here. So 1/2 squared is 4, -2/4 is the -1/2 you see right here. So that way we just have a binomial squared to worry about. The rest of this is pretty straightforward right here. But so anyway, you can see, folks, and again, I didn't show every last step, but if you cube the first term, you get 27. Now this is going to be, and again, I could have shown one more step here. This would be the 3a squared b term. In other words, the second term here in this binomial, cubing this binomial, is 3a squared b. And this is what you get when you do that. It would be 3 squared times 3, and the b is √5. And right here, it ends up being 45. And then the square root of 5 cubed is √5 times √5 times √5, but 2 of those √5s just give you a 5. So you may want to check this, but I've double checked it. And again, I apologize for not showing all the steps. It just gets a little tedious. And in a similar fashion, going from here to here, I expanded this binomial to get these 3 terms right here. All right. And it didn't take long after that to show that this was indeed a solution. But you can see doing this solution is almost as long as the problem itself. If you guys have done this before, once you find your first rational zero, you can use synthetic division to get a second degree polynomial, which is a quadratic that you can solve pretty quickly. And so literally, I think you can solve this problem in less time than it takes to actually check the solutions. And so I don't know, I haven't, with colleagues I used to work with, very few of us ask the kids to do this. Most of the time, just let them use a calculator, which really it doesn't help their critical thinking. But again, it's just very time prohibitive. I skipped steps, and this took me around 10 or 15 minutes, maybe closer to 20 minutes to get this done. So, but again, you may want to double check my steps here, but it did work out to 0. And the last step was pretty easy here. 4√5 minus 3√5 minus, these two terms right here combined to give you -4√5. These two terms right here. And of course, that offsets the positive 4√5, and of course, the 9's offset. So again, just thought I would do it once, and it'd be nice to know kind of informally how many of you instructors actually have the kids do this. Maybe once, but again, on a test, it's asking a little bit too much. All righty. Thanks for listening.